Well, thanks for joining today for the 8th day of 12 Days of DevRel with Hazelcast. I'm your host today, Melissa Chang, and today joining me, our senior architect, Charles Harris. Hey, Charles, how's it going?
Awesome, Mel. Thanks. How are you doing?
I'm good. It is Friday, and I'm super excited for this session. If you're live with us or tuning in at a later time, let us know where you guys are tuning in from in the chat. I'm super excited for your architect session today, Charles. But before we dive in, I'd like to have you introduce yourself to the community. Can you let us know where you are tuning in from today and let us know a little bit about your background and how long you've been at Hazelcast?
Yeah, awesome. Thanks for having me, Melissa. Hi, everyone. My name is Charles. I'm a senior architect at Hazelcast. I've been working at Hazelcast for a little over 2 years now. I'm tuning in from Los Angeles. I've been here I've lived in LA for 10 years now. And before this, I worked at Oracle and I have a degree in biomedical engineering.
Awesome. Well, I don't want to take any more time. I just want to quickly remind everyone, if you haven't already, don't forget to sign up for our big 12 Days of DevRel raffle of $500 gift card to Amazon. Winner will be selected on the last day on the 12th. And feel free anytime during the session to ask any questions by dropping them into the chat, and we'll respond live at the end during Q&A. Now, without a further ado, over to you, Charles.
Awesome. Thanks, Mel. Okay. Oops. Okay. Can you see this okay?
Yep.
Okay, thanks everyone. So today's architect session is we're going to be talking about internode communication and we're going to be using pub sub messaging structures. So here's the plan for the presentation. I'm going to give a very brief overview of Hazelcast. I expect that most of you already know how to use it, but for those that don't, I'm going to give you, a really quick summary of what we are and what we're used to do. Then we're going to dive into the specific context and use cases for this pub sub messaging architecture. We'll take a look at one specific architecture for achieving these types of use cases, and that's going to involve a global messaging layer. Then we'll look at the pros and cons of this architecture. Then we'll look at a second example, and that's going to be a replicated local messaging layer. We'll look at the pros and cons of this type of architecture too, and then we'll go into questions. And I know I have questions and Q&A at the end here, but please, if you have any questions before that, feel free to stop me, and I'd be happy to answer them live. So here's a quick overview of Hazelcast. Hazelcast is a unified real-time data platform, and what that means is that we have stream processing and distributed in-memory data storage capabilities all within the same platform. So pretty much any need you have for a real-time system, we support it in one set of binaries and one code base. Today, we're not really going to be talking about the stream processing portion of Hazelcast, although that is a large set of capabilities that we have. Instead, we're going to drill down into this fast data store capability, the distributed in-memory storage. Specifically, we're going to focus primarily on the pub sub type of data structure. So this is going to be topics, reliable topics, and queues. Most of the time, the most commonly used data structure is actually key value store maps. And those will actually be involved in these architectures as well. But again, the focus is going to be on pub sub data structures and use cases. So the context for this presentation is that we're going to be focusing on a situation where you might need to exchange messages between a producer and a consumer connected to different locations. So some example use cases where this might be used: package tracking, real-time delivery updates, user chat, customer support. So in all of these situations, there's a lot more possibilities where you might run into the situation than just these four listed, but these are just some examples. And in each of these situations, you might have a message that is sent from one location and needs to go to another location, but the recipient of that message may not be connected necessarily to, there's only going to be one place that they're connected, and somehow we have to design our architecture to figure out where that person's connected. And so we're making sure that the recipient is connected to the same place where the message is actually being processed. So let's take a look of how we would actually do that. So with this type of pub sub messaging architecture, there's two problems that we're really solving for. One is that we might have people in different geographic locations that need to message each other. So we have to make sure that the message gets there. But even further than that, to get a little bit one step more advanced, we also have to make sure that the person receiving the message is only getting the messages they're supposed to receive. Because in a large scale enterprise grade messaging architecture, there'll probably be tons of messages on each node, but we only want the recipient of each message to be able to see the message addressed to them and not to be able to see all the messages. So that's another technical challenge that we're going to talk about how to address that today. So, from a high level, this architecture that you see here is a pretty traditional mobile app messaging architecture, and it just uses Hazelcast as a global backend infrastructure handler. So we have a mobile app, and we have four different locations. So you can think about just imagine in your head we're focusing on the United States, and we cut the United States into four different geographic regions, and we have a group of users in location one, a group of users in location or region two, a group of users in location three, and a group of users in location four. So anyone, for example, that's on the West Coast of the United States will be hitting the location one group of services, and anyone on the East Coast of the United States will be hitting this location four group of services. So there's a couple reasons you might want to do that. First is that if you need to do any kind of upgrades or updates or transformations to your system, you can do it one location at a time. And if downtime is required, you're only affecting part of your user base and not the entire messaging system. Second, you're minimizing the distance between the service and gateway layer here and your actual mobile app users. And that's going to reduce end-to-end latency for this specific part of the system. So there's a few reasons why you might want to break your service tier into geographies like this. Um, and that's kind of the situation that we're addressing here today in this presentation. So in this case, let's, for example, take the case where we have an application and we want to enable some kind of functionality that allows for direct messaging between user one and user four of our platform. So we have user one, let's just say they're in location one, and we're going to have another user, but let's say we don't know exactly where the second user is going to connect to yet. So we don't know where to send the message. Well, at a high level, this is a pretty traditional architecture. So we're going to be using HTTP and probably WebSockets for bidirectional communication. So we can send a request to a mobile API gateway, and this API gateway is going to make a gRPC call or a REST call to our service tier. And our service tier is likely going to consist of more than one service. It's likely going to have services that are publishers and some services that are consumers. When you send a message, that's going to trigger our set of services that are actually going to be publishers. And that publisher service will then, via Hazelcast pub sub mechanism, actually write this data to Hazelcast, which will then eventually be consumed by one of these different service tiers and feed them and push the message back up to the mobile app user that's at that location. Now, the trick is, how do we avoid sending messages to every single one of these locations every time we send a message? Because what we don't want to have is someone at location one send a message and then it pushes that same message to every single location, even though our recipient is only connected at one of those locations. So if we publish it to every single location, you can work with that, because you're guaranteeing that no matter where the recipient is connected, that they'll get the message. The problem is that it's going to completely clog your network, and you're going to be reading, 4, 5, so 10, however many different locations you are. You multiply that number of locations, and that's how many times more messages you're reading than you actually have to be reading. So how do we make sure that the message is only getting to where the recipient connects? And part of that is going to have to be handled in our application logic. So one thing we could do is, if you imagine the case of a direct message, say we have Bob and Joe. Bob is the sender of the message, Joe's the receiver of the message. Um, Bob would publish this message, and it'd go through the service tier and it'd publish to Hazelcast. And what the publishing service would do, or what I would expect it to do, is to create a topic with a topic name, and also at the same time that it would create this topic, it would also subscribe to the topic, because we'd probably want to hear what Joe has to say back to our message. And on top of that, it would also create a hash map. In Hazelcast, these hash maps are called IMAPs, and they're built off of traditional Java hash maps, except we've made them distributed and higher performance. So not only would we be creating a topic and subscribing to it as part of this publish service, we'd also be creating this hash map that would create a map of active connections and active topics. And we'd also probably store some other information, such as the intended recipient of that message, maybe when the topic was created. And we'd also probably keep some kind of cursor that told us when the last message that was sent or that was received by the recipient. So we're only publishing the latest message in the topic, and we're not pushing every message that has been sent to the topic every time that the recipient is ready to read from the topic. So then what happens is we have Joe. Joe's going to be the recipient of this message. We don't know where Joe logs in. Let's just say he logs into location 3. So when Joe logs into location 3, he's going to trigger the consumer part of your service tier through the same socket gRPC type of mechanism that we had before. And what you need to do now is, in the consumer service, you're going to have to include some kind of application logic that's going to do a lookup on this map. And in the case of a direct message, one thing you might be able to do is look up any recent topics that were, let me rephrase, any recent references to this topic that were created in the hash map, and do a lookup for that topic name. And then if you find something in the lookup, then what you do is you would subscribe to that topic name as part of the service activity. And once you're subscribed to that topic name, then automatically those messages will get pushed from the topic back up through whatever location you're at, all the way back to your mobile app user. And so that's kind of how you control, and that's how you avoid publishing messages to every single location. But you also, get the benefit of using Hazelcast. So the reason you would use Hazelcast for this specific situation is, one, because you have both that ability to store hash maps and you have the ability to store pub sub architectures. So you can do all this in one system. But also, Hazelcast is in memory. So this message transmission and this message receipt is very, very fast. On top of that, you also have the reliability of the fact that Hazelcast is distributed, which means that you have an element of high availability already built into the product. And on top of these already good things, we also have an API that's going to asynchronously save these message chains to an underlying system of record. So this will probably be a relational database. So not only do you get the performance and the reliability of a distributed in-memory system, but you're also going to get the security and the durability of a database that's backing up these message chains for these message threads that need to be a little bit more durable and a little bit more permanent. And so with Hazelcast, you really get the best of all worlds with this architecture. And we'll look at pros and cons of this in a second. But in the second architecture, we're even going to see how to make this even more scalable, so you can really get an enterprise grade system where we're designing things that get 10 millions of active users. And that's how these big companies with lots of messages are going to handle this type of workload. They use things like Hazelcast, and they use things like these architectures that we're discussing. And we'll go into that a little bit more detail in a second. So does anyone have any questions about this so far?
One question that we'd like to ask is, why would we not use a database for this use case?
So that's a really good question. So one of the reasons you wouldn't want to use a database for this use case is because the database is going to be disk-based, and the database is not optimized for high amounts of concurrent reads and writes. and it's much harder to scale the database. So it's really going to be a question of performance here. So databases are durable and they are reliable. So it makes sense why you'd want to consider using a database. But ultimately, Hazelcast is going to be the better option for the performance and for the scalability. And because you can back all this stuff up in a database anyway, but put Hazelcast in front of that database to give um, the performance to this type of architecture that you need to address millions of users.
Nice. And second question, why would you not use Redis for this use case?
That's another good question. So Redis is also a distributed in-memory store, but you wouldn't necessarily use Redis for this architecture because Redis is it's not peer-to-peer. Hazelcast is a peer-to-peer architecture and Redis is a master worker architecture. That means that in your Redis cluster, some of the nodes only support reads and some of the nodes only support writes. In a pub/sub type of architecture, you have lots of reads and lots of writes. It's a lot closer to a 50-50 type of ratio than a traditional caching use case, which might be 70% reads and 30% writes. And because of that, Redis for this type of pub sub architecture is not going to scale the way that you need to in order to make this a really performant, reliable system. Although it is in memory, so the memory part will work fast. It's just going to fall over if you add too many of these users at one time, and it won't be able to handle the workload.
Got it. And one final one and another one. Why would you not use Kafka?
So that actually hits on an interesting point. So you could certainly use Kafka for this use case. The problem with using Kafka for this use case is that in order to make this work using Kafka, you would likely have to have a consumer group for every single one of these locations. And so what that means is that that falls into the trap we discussed before that every time you publish a message to Kafka to be distributed, that it would publish to every single one of these locations. And that's the only way that you could guarantee that your user got this message because there's no storage tier in Kafka. It's all just going to be complete pub sub. And so there's no way to add that extra intelligence like we talked about with the hash map where you're keeping track of those active connections. And so that's going to clog your network. And there's also some kind of care you have to take when dealing with consumer lag by having this many concurrent Kafka consumer groups. Those are really good questions. Thanks, Mel.
Yeah.
So let's look at the trade-offs of this architecture. So the pros, first of all, of this architecture is that there's minimal infrastructure footprint. As we saw, there's only one Hazelcast cluster. So this means less infrastructure to support that cluster. It means minimal cost because it means you're paying for less infrastructure, so that's less cost. And it's also easier to manage because there's less nodes in total to manage. And that's just easier on your DevOps teams. The cons of this kind of architecture is that there is a little bit of client separation. And what this means is that you're putting the service tier and the gateway close to each end user. So that's good from a latency from that perspective. However, you would have to find a global location for Hazelcast that's sort of geographically centered between all your client locations. And that is possible, but that will lend itself to slightly higher latency because just the distance between the actual server and each client is going to be a little bit bigger than it needs to be. And so you might have to think about how that's going to affect the time it takes from the data to actually end up at the end user. It also means there's a single point of failure in the Hazelcast system. So Hazelcast is distributed. So there is resiliency built in. So for example, if you lose one Hazelcast node or two Hazelcast nodes, depending on how you have backups configured, you can still, keep going with no downtime and maintain without, all your data without losing anything. However, if for example, you lost all of your Hazelcast nodes at once, that entire system would be defunct and you'd have to figure out, your disaster recovery strategy from there. So in this case, Hazelcast would be a single point of failure, but that would also be the case no matter which backend store you're using for that type of architecture in that fashion. So let's talk about a second architecture. This is very similar to the first one we discussed, but instead of having one global Hazelcast tier, now we have a replicated local tier. And so, it's the same mechanism where we have users sending requests over sockets and HTTP, and this is making a REST call to our services, and our services are publishing and consuming, and we have our hash map that shows active connections, so we know which group of cells to send our data to. The difference is that each individual user is going to connect to their own Hazelcast instance. And this is going to reduce latency. And the way we handle this is we're going to replicate both the data in our hash map every time it's created and our messages and our topics to all of the other Hazelcast instances in the local geographic regions. And depending on exactly which data structures we're using to do this, we're either going to do it using a stream pipeline or Hazelcast's built-in WAN replication tool, which allows you to asynchronously replicate data from a Hazelcast IMAP to another Hazelcast IMAP. And all the while this is going on, we're going to have multiple copies of our system of record, one local copy in each place. And we're going to back up the data from the hash map and the data from our messaging topics and queues into the system of record as we go for, again, that reliable, durable, persistent feel that we might need for some types of messaging architectures. So are there any questions about this one so far? No.
Sorry, could not find the one. One quick question. Should we embed Hazelcast into our microservices with this architecture?
So you can embed Hazelcast into your microservices, and that will work. However, I strongly advise against it in this use case. And the reason I advise against it is because in this case, usually in messaging architectures, you're not actually storing too much data. And so it's very common that you will need to scale your services tier for compute functionality um, a lot more than you'll need to store Hazelcast. And so the whole goal of the microservice architecture here is to make your microservice architecture stateless. And you do that by separating the state in Hazelcast and the actual service part in the service tier. And so doing this actually allows you to scale just the part of the system that needs to be scaled, which is likely going to be your service tier, not Hazelcast, because Hazelcast is really robust and it's really performant and it's designed for these kinds of workloads. So you might only need 3 Hazelcast nodes in a cluster, but you might need 10 nodes in your service tier. However, if you embed your application in Hazelcast, then you'll need 10 nodes of Hazelcast regardless, and that adds unneeded complexity to the system.
And last question, how scalable is this
So
solution?
this solution is very, very scalable. Um, and the reason for that is it's more scalable than the last example because you have multiple Hazelcast instances. So, say you have 10 million users, you can break those 10 million concurrent users across multiple backend infrastructure instances, and you don't have them all hitting one instance. So when you design the architecture like this, you can really handle multiple concurrent messages, both subscription, both publishing and subscribing to those messages, with the expectation that this backend infrastructure and this intelligent application layer that you put in here will be able to handle this design. So it is very, very scalable. Thanks, Mel, for the
Awesome.
awesome questions.
Yeah.
Um, so yeah, so that's good. Let's look at some trade-offs for this one. So the pros of this type of architecture is that you've got higher performance and lower latency because the clients are going to be geographically so much closer to the actual server in this type of architecture. You've got increased resilience because say one Hazelcast entire cluster goes down, it's only going to affect a couple of your users and not all of your users. You also don't lose any data because all of the data is going to be replicated across all these other clusters. So you can easily, if you in the event you lose a cluster, you can easily bring it back up, and then all of that data from all of your other clusters and all your other regions will automatically sync to the one that you just brought back up. And it's also highly scalable, like we just talked about. The cons, and this is where you need to think about what your exact requirements are for the solution, is that you've got a much increased infrastructure footprint. This is going to lead to a significantly higher cost than the last type of architecture. And now you've got a lot more moving pieces and a lot more coordination to keep all of these different service tiers and all these different Hazelcast instances and different pipelines and replication mechanisms in sync. But if you're up to the challenge, this from a technical perspective is definitely the way you want to do things. And so with that, that brings us to the end of the presentation. I don't know why there's a random Z in the middle of the slide. But if anyone has any questions, feel free. I'd love to have a Q&A if there's anything else you'd like to know.
Well, while we wait, let's finish with some fun rapid fire questions. And feel free anytime during this time to add in questions, um, and we'll answer them as they come in. But Charles, coffee or tea?
I actually don't drink either coffee or tea, so I prefer neither. I try and avoid the caffeine. I like both of those drinks, but I don't really drink either day to day.
And iOS or Android?
That's a hard one. I think I have to go iOS. iOS because it's just a lot more intuitive for me to use. I think if I had to develop an application, I'd prefer developing for Android because I think the hardware actually performs a lot better than the iPhones.
And since we're both from Cali, NorCal or SoCal?
I've lived in SoCal for 10 years, Mel, but I actually prefer NorCal. I'm from NorCal, and so I have an emotional attachment to the place. And I'm from Sacramento, and I love it up there. So I'm gonna have to say NorCal.
Nice. Me too. What is your favorite football team?
Favorite football team? Are we talking about American football or soccer?
Oh,
Football like the rest of the world sees football.
I'll do American football.
Okay, American football, Cincinnati Bengals. My family is from Cincinnati, and so I'm a diehard Bengals fan. I know there's a lot of Steelers fans out there, and so I hope my answer doesn't antagonize anyone. But yeah, go Bengals.
It's okay. I'm a Cowboys fan, so
Oh
that's
no,
always
yeah, that's yeah, controversial.
yep. Morning meetings or afternoon meetings?
Definitely morning meetings. I'm super productive in the mornings, and I definitely start tapering off in terms of focus around 1 or 2 p.m. So I love getting meetings in the morning when my mind is still at the sharpest.
True. And last one, pizza or pasta?
Oh my god, both, but definitely. I can't say definitely either. I'd say I like the taste of pizza better, but for a more blend of, like, health and taste, I would go with
Oh,
pasta. But if I had to eat one thing before I die, it'd be pizza out of those 2.
what kind of pizza?
Anything but mushrooms. So, like, pepperoni,
Ah,
onions,
nice. The
peppers.
classics.
Yeah.
Awesome. Thanks. Well, if you have any questions, this recording will be on demand. And so feel free to add any of your questions in the comments so Charles can answer them. Feel free to add us on community Slack and ask us any questions there. We will be there to respond. But thanks all for joining today. And thanks, Charles, for your session.
Yeah, thank you so much for having me.